Okay, so now we will study that single phase transformer. Of course, headline it is written as transformers, but we will study single phase transformers only, and after this we will see that your three phase induction machine only in brief, and then the DC machine, mainly DC motors, right. So, generally if you look at this thing, a transformer is a device which uses the phenomenon of mutual inductance to change the values of alternating voltages and current, right. So, basically in a transformer, that one of the main advantages is that it can transform the voltage level, that is, it can increase the voltage level, or it can, or what you call, decrease the voltage level. So, this is actually what you have, the transformer, right. So, it can your what you call, for example, many, when you look at the your power station, transmission line, distribution line, there are different voltage level, and those voltage steps are, or steps up or step down only by using your what you call the transformers, right. So, that means, therefore, the transformer is a device which uses the phenomena of mutual inductance, mutual induction to change the values of alternating voltage and current, right. So, losses in transformers are your generally low, and therefore, efficiency of the transformer is very high. Losses we will see later. So, being static, they have a long life and are very stable. So, transformer is a static device. So, now for example, suppose if you consider your what you call a ferromagnetic core, and you have your primary, this side we call primary side, say you have n1 number of turns, here it is n1 number of turns, and you have the secondary, you have n2 number of turns, and in the secondary load is also connected, but shown is dash line, that means load, say when load is not connected. Now, an alternating supply voltage, say V1 is given, right. So, when load is actually not connected, so what will happen is very small current, right, will flow through this your what you call, through this primary side of the winding, and the flux will link actually both the primary as well as the secondary winding, when this side is your what you call open circuited, right. That means, load is not connected. So, no current is flowing through the your what you call secondary, but primary side you have applied your small voltage, right. So, small current called exciting current will be responsible actually for your producing the flux, and direction of the flux you will get the magnetic circuit, the right hand rule I told you. In the direction of the current, you grasp the your what you call coil, and your thumb will put the your what you call the direction of the flux, right. So, let me clear it. So, this is actually ferromagnetic core, and this is your circuit symbol of a transformer. So, primary winding is connected to AC supply, I told you, and secondary winding may be connected to a load. Now, principle of operation: when the secondary is an open circuit and an alternating voltage V1 is applied, I told you, to the primary winding, a small current called no load current, that is I0 flows, right, which sets up a magnetic flux in the core. That means, here it will set up the magnetic, suppose a small current, here it is showing I1, because it is primary side, we are putting V1 voltage, I1 current, but here it is I0 current when it is a no load, right. At that time, I1 is equal to say I0, and your which sets up a magnetic flux in the core. This alternating flux links with both primary and the secondary coils, right, that I told you, and induces in them an EMF of E1 and E2 respectively by mutual induction. That means, here actually here this is supply voltage anyway. For an ideal transformer, a voltage will be induced. Say if I make it like this, it is E1, right, but at that time we have to see different way, that this winding also has your resistance as well as that your what to call reactance, right. So, we will see later. So, let me clear it. So, in that case, your E1 and E2 respectively by mutual induction. So, the induced EMF E in a coil, if you have n turns, is given by E is equal to minus n d phi by dt. So, from the Faraday's law, the voltage induced thing is n d phi by dt, and Lenz, your what you call Lenz law will give you the your direction of the EMF. So that's why minus sign is here. So following assumptions are made for an ideal transformer. Winding resistance say are negligible, say there is no winding resistance. All the flux produced is confined to the core of the transformer and links fully both the windings. There is no leakage of the flux. We are assuming there is no leakage and the flux links both the winding fully. Number 3, the permeability of the core is very high, right, so that the magnetizing current required to produce the flux and establish it in the core is negligible, right. And number 4, that is D part, hysteresis and eddy current losses are negligible. These are the 4 assumptions we have made, right. So these are the 4 assumptions we have made for an ideal transformer. Now in an ideal transformer, dψ by dt is same for both primary and secondary winding, because the flux phi linking both primary and secondary winding. So U1 is equal to, we can write minus N1 dψ by dt, that is the induced voltage in the winding. Similarly, E2 is equal to minus N2 dψ by dt. And we are neglecting your what you call the ideal transformer, your resistance is neglected. Now therefore, if you divide U1 by E2, you will get N1 by N2. Therefore, if you divide these two equations, E1 by E2, you will get N1 by N2. Therefore, E1 upon N1 is equal to E2 by N2, that is induced EMF per turn is constant, that is E1 by N1 is equal to E2 by N2. Now polarity of the induced EMF is given by Lenz's law. Actually it opposes the change, hence it is actually negative, right. From your higher secondary physics you have gone all through this, right. So assuming that no losses, therefore we can make V1 by N1 is equal to V2 by N2. So in that case, if we assume that there is no loss, then we can make V1 by V2 is equal to your N1 upon N2. Here it is E1 upon E2 is equal to N1 upon N2, right. And if there is no loss, we assume there is no loss, then we can write that your term supplied voltage, that is V1 by N1 is equal to V2 by N2. This is primary side voltage and V2 is the secondary side voltage. Therefore, we can make V1 by V2 is equal to N1 by N2 is equal to K, that is called turns ratio. Therefore, K is the voltage ratio or turns ratio or transformation ratio. Therefore, V2 is equal to V1 upon K. If K less than 1, then it is called step up transformer, and if K you are greater than 1, it is called step down transformer. So let us go back to that your circuit again. Here let us go back to the circuit again. So we are assuming there is no loss, right. So and this side is voltage V1, this side is voltage V2. That means this is if it is marked that this is my E1 and here also it is my E2, we are assuming there is no loss. Therefore, your V1 by your U1 by E2 is equal to N1 by N2. So is equal to your V1 by V2 is equal to N1 by N2. Later we will see the relationship between V1 and U1 similarly here. So will be here only, right. So if K less than 1, that is step up transformer. If K greater than 1, that is step down transformer. For example, suppose say N1 is equal to say 50, right, and N2 is equal to say your 100, right, 50 turns and 100 turns. Then K is equal to N1 by N2 is equal to 50 by 100 is equal to half. That means K less than 1, that is your K less than 1, because it is half, that means it is step up transformer. Why it is step up transformer? That means here then V1 upon V2 is equal to K is equal to half, right. That means V2 is equal to 2 into V1, right. That means it is step up transformer, because primary side voltage, if it is V1, secondary side it is becoming 2 into V1. For example, primary side if it is 100 kV, then secondary side it is 200 kV. So it is a step up transformer if K less than 1. Similarly, for if K greater than 1, then it will be step down transformer, right. So that is k greater than 1 for step down transformer. Now, when a load is connected across the secondary winding, a current I2 flows, right. So, in an ideal transformer, loss, whenever I am telling this, first you draw those circuit diagram in the beginning, right, that ferromagnetic material, the core, the winding, first you draw it, then you see this. When a load is connected across the secondary winding, a current I2 flows. In an ideal transformer, losses are neglected and a transformer is considered to be 100% efficient, right. Although in reality ideal transformer is not possible, but for the sake of our clarification. Now, hence the primary and secondary volt amperes will be equal, that is V1 into I1 must be equal to V2 into I2, that is V1 actually is your primary side voltage and I1 is the primary side current and V2 is the secondary side voltage and I2 is the secondary side current. Therefore, their volt ampere must be same, that is V1 I1 is equal to V2 I2. Therefore, V1 by V2 is equal to I2 by I1. So, V1 by V2 is no N1 by N2. So, is equal to I2 by I1 is equal to N1 by N2 is equal to K. Therefore, either you can write V1 by V2 is equal to N1 by N2, or in the case of current it will be I2 by I1 is equal to N1 by N2, that is N1 I1 is equal to N2 I2, right. So, that means MMF on the, I mean if you later will see it will be different way. Suppose if it is I2 by I1 is equal to your N1 by N2 for cross multiplication, therefore I2 N2 is equal to your I1 N1, right. Therefore, MMF on the secondary side must be equal to the MMF on the primary side, right. So, the rating of a transformer is stated in terms of the volt ampere that it can transform without your overheating. So, this way we make it, that volt ampere. Now, transformer rating is either V1 I1 or V2 I2, when I2 is the full load, say secondary current. So, this is actually transformer rating. Generally on the transformer nameplate you will find its KVA rating will be given, right, its frequency will be given, per unit impedance will be given, all these things will be given. So, just to whatever little bit we have studied, we will come to phasor diagram other thing later. You take a small example, an ideal transformer has a turns ratio of 8:1 and the primary current is 3 ampere, it is given. When it is supplied at 240 volt, calculate the secondary voltage and the current, right. So, now turns ratio is given 8:1 means it is N1 is to N2. I mean whenever it is given that 8:1, that means it is N1 is to N2 is equal to 8:1. So, N1 by N2 is equal to 8 by 1 is equal to K. So, K is equal to 8, that means it is a step down transformer because K greater than 1, right. So, that means V1 by V2 is equal to K, therefore, V2 is equal to V1 upon K. So, 240 by 8, so V2 will be 30 volt. So, primary side is 240 volt, secondary side is 30 volt. Also, we know that I2 by I1 is equal to K. So, I2 is equal to K into I1, it is given I1 is equal to 3 ampere. So, I2 is equal to 24 ampere. So, interestingly if you see this side it is your 30 volt, right, load voltage is low, but at the same time current has increased because volt ampere has to remain your same. So, if you see the volt ampere primary side 240 volt into 3 ampere current, so 720 volt ampere, right. Similarly, for your secondary side, if you look into the secondary side also has to be 72. So, if you see this voltage is your voltage is your V2 is 30 volt and this is 24 ampere. So, that is also 720 volt ampere, right. So, that means V1 I1 it has to be equal to V2 I2, right. Now, another small example. So, a 5 kVA single phase, it is 1/5 source actually single phase. Single phase transformer has a turns ratio 10:1, that is N1 is to N2 is equal to 10:1 and is fed from a 2.5 kV supply, 2.5 kilovolt, right. So, neglecting losses, determine A, the full load secondary current, B, the minimum load resistance which can be connected across the secondary winding to give full load kVA, and C, the primary current at full load kVA. So, these are the things have been asked to do it. So, first thing is that N1 by N2 is equal to 10:1, 10 by 1 is equal to 10. Now, V1 is given 2.5 kV, so 2500 volt multiplied by 1000. We know it, since N1 by N2 is equal to V1 by V2, therefore, V2 is equal to V1 into N2 upon N1, right, is equal to V1 is given 2500 and N2 by N1 is 1 upon 10. So, it is 250 volt, right. So, V2 is the 250 volt. The transformer rating in volt ampere will be V2 I2 at full load, right. So, it is V2 is equal to your V2 I2 is that is kVA is given 5000. I mean, this is something like this. So, transformer rating at full volt ampere is equal to V2 I2. So, this 5 kVA is given. So, 5 into 1000 volt ampere is equal to V2 is 250 volt. We got V2 is equal to 250 volt into I2, from which if you solve you will get I2 is equal to 20 ampere, the full load current. So, kVA it is given in the problem, it is given 5 kVA, that means 5000 volt ampere is equal to voltage is 250 volt here and current you have to determine. So, from which you will get I2 is equal to 20 ampere. Now, B is minimum value of load resistance. So, RL is equal to just V2 by I2. So, V2 is given 250, we got 250 and I2 we got 20. So, it is 12.5 ohm. C is N1 by N2 is equal to I2 by I1, we know that. Therefore, I1 is equal to I2 into N2 by N1. So, I2 we got 20 ampere and N2 by N1 is 1 upon 10. So, it is actually 2 ampere, right. So, very simple, very simple. Now, next is no load phasor diagram. Now, the core flux, actually no load phasor diagram, the core flux is common to both primary and secondary windings in a transformer, that I showed you in the beginning, and is thus taken as the reference phasor in a phasor diagram. For example, in a phasor diagram, this is the flux, right. We will assume that phi is equal to, say, sinusoidal variation phi m sin omega t, right. This is your phi m sin omega t, this is the flux and we are taking the your phi as a reference. Now, I0 is equal to small no load current and loss is neglected, right. So, primary winding then will be a pure inductor, because we are giving alternating supply to the primary winding. So, if our loss is neglected, so it will act like your what you call that a pure inductor. So, in that case what will happen, that whenever you say that as per your what you call as per Lenz's law, right, we know that U1 is equal to minus, for the primary winding it is N1, right. So, into d phi by dt, right. This minus sign comes because of the Lenz's law, right. So, this is U1 is equal to minus N1 d phi by dt. Now, if we know phi is equal to phi max sin omega t. So, if you just take the derivative of that, then you will get U1 is equal to minus N1, then phi m, then omega, then your cosine omega t, right. That much that you will get. So, this one you can write that your minus N1 phi m, say omega, this is cosine omega t. So, we can write sine 90 degree minus omega t, and this minus sign is here, this minus sign is here, you take minus side inside that, then what you will get, that U1 is equal to your N1, then phi m, then omega, right. Then you can write sine omega t minus 90 degree. So, sine omega t minus 90, that is U1, right. That means, if phi is equal to the reference, that is your sine omega t, right, and it is a loss is neglected, therefore, that no load current I0 also will be in phase with your what you call in your what you call with the flux, right, and I0 actually will lagging from your V1 by your 90 degree. If loss is neglected, if it is loss is completely neglected, right. So, in that case I0 will be in phase with phi, and your as it is as resistance is neglected. So, generally that therefore, the I0 is lagging from the voltage V1 by 90 degree. It is because that primary winding is acting as a pure inductor, right. And if you take the magnetizing, we call magnetizing reactance, right, Xm, then you will see that I0 is purely, if R is loss is neglected, then this I0 and phi both are in phase and lagging from V1 by 90 degree. So in this case, that U1 is equal to is coming omega t minus 90 degree, and that means phi is equal to phi m sin omega t, and here it is sin omega t minus 90 degree. That means, so I am clearing it, right. So that means my U1 will be your what you call lagging from phi by 90 degree. Therefore, this is my U1, this is my U1, the primary induced EMF. Similarly, E2 also will be the same way, E2 also will be lagging, and E2 is equal to V2, because loss your what you call, we are considering an ideal transformer, right. So this is your secondary induced EMF, both will be like this. Now, therefore, the supply voltage from the Lenz's law, as it opposes the change, right. So Lenz's law, it is actually V1 is equal to minus U1, right. So and U1 is equal to minus n d psi by dt. That means my V1 will be n, it is in general it n1 your what you call d psi by dt, because U1 is equal to minus n1 d psi by dt. So minus minus plus, it will be n d psi by dt. Therefore, my V1 will be is equal to n1, phi is equal to phi m your what you call sin omega t. If you take the derivative, it will be n1, then phi m, then omega, right, then cos omega t, right. So that will be your what you call V1. So if you your what you call this cos omega t, if you write like this, for your just understanding, if you write like this, somewhere I am writing, hope you will be able to read it, that your V1 is equal to your n1, then phi m, then omega, and this is cos omega t. Two way you can write, one is sin 90 degree minus omega t, another is your sin 90 degree plus omega t. That means we can write sin your omega t plus 90 degree, right. That is my V1. That means this is my phi is equal to phi m sin omega t. That means this V1 actually leading this phi by 90 degree, and V1 is equal to minus E1. So this is my your E2, this is E1, and this is your V1 is equal to minus E1. So that then E1 is the primary induced EMF, and V2 is the your E2 is equal to V2 is equal to secondary induced EMF. So this is actually V1 is equal to minus E1. So basically your I0 will be in phase, your loss is neglected with the your in phase with your what you call with the flux phi. Phi is the taken as a reference, right. Therefore, let me clear it. Therefore, I0 produces the flux and in the phase with the flux. Now, the primary induced EMF E1 is in phase opposition to V1 by Lenz's law, and is shown 180 degree out of phase with V1. So this is E1 and this is V1 is equal to minus E1. So 180 degree out of phase. So this is Lenz's law, and this Faraday's, all these things you have studied in your higher secondary physics, right. So this is how that your when we are not considering the losses. So this is the phasor diagram. Now generally what happens in a transformer, that heating of the core happens because of your what you call that energy losses due to your hysteresis and eddy currents, right, flows in the core. So because of that, some loss component will be there. If you consider the loss component, then I0 actually is not exactly lagging 90 degree from V1 or not exactly in phase with phi 1, there will be some lagging angle of I0. So that's why your whenever you have such thing, right, that in this case what will happen, that your this I0 actually not exactly in phase with I, right, because it has some core loss, that is iron loss, that is eddy current and hysteresis loss. So because of that, your this is V1 is equal to minus E1 is okay, but this I0 actually lagging by an angle phi 0 from V1. So this angle is phi 0, and its your what you call its component along phi is Im is equal to your I0 sin phi. This component is responsible for producing that your no load flux, because this is phi 0. So it is cos 90 or what you call that your I0 is equal, your Im is equal to I0, right. It will be cos 90 minus phi 0. So it is I0 sin phi, and this IC will be I0 cos phi 0, right. So, this component actually basically it will give your coal loss or iron loss at the no load condition, right. So, total coal losses is equal to basically iron losses, hysteresis and eddy current losses. So, that is why I 0 is not exactly is in phase with phi, but this angle actually, this angle I phi 0 actually quite large. So, that is total coal loss is equal to iron loss is equal to V 1 I 0 cos phi 0, right, and this and I told you this I 0 cos phi 0, that is I c actually is equal to I 0 cos phi 0, that means this component, that means I 0 cos phi 0 actually is equal to your I c, that means V 1 into I c, that is your total coal loss or iron loss, right. So, this is the no load phasor diagram for a practical transformer. Now, if current flows, the losses will occur when losses are considered. I 0 has two components, I told you everything. I m we call the magnetizing component and I c the coal loss component. This magnetizing component at no load is responsible for producing the flux. So, eddy current loss, that is coal loss component basically is supplying eddy current and hysteresis losses. This eddy current and hysteresis in the magnetic circuit I have given you those formulas, right. So, this is nothing, this is nothing, later will come, right. So, now this is for this numerical a 2400 by 400 volt, it is a step down transformer because this is primary side 2400, is secondary side 400 volt. So, this is a step down transformer, right. So, N 1 by N 2 actually is equal to 6, we call V 1 by V 2. Single phase transformer takes a no load current of 0.5 ampere and the coal loss is 400 watt, that is coal loss is given, that is V 1 your I 0 cos phi 0, that is your coal loss 400 watt is given. Determine the values of the magnetizing and coal loss component of the no load current and draw the phasor diagram. So, it is given V 1 is equal to 2400 volt, V 2 is given 400 volt, I 0 is given 0.5 ampere. So, core loss, that is iron loss, is equal to also given 400 watt. Therefore, V 1 I 0 cos phi 0 is equal to 400. So, that is 2400 into 0.5 cos phi 0 is equal to 400. Therefore, we will get cos phi 0 is equal to 1/3. Therefore, phi 0 is equal to 70.5 degree. Now, magnetizing current I m will be 0. I 0 sin phi 0. So, 0.471 ampere because phi 0 is equal to 70.5 degree and coal loss component I c I 0 will be 0.167 ampere, right. And as this current is lagging, if you write in your phasor thing that your I 0 will be equal to actually I c minus j I m, right. So, I c is equal to 0.167 and minus your j 0.471, right. If you take your V 1 as a reference, so this current actually lagging from your what you call the voltage. So, it will be minus sign, right. This is your real part and this is your imaginary part. This is coal loss component current and this is your imaginary loss, magnetizing, the imaginary part is a magnetizing component of the current. So, now this is the phasor diagram, this is your V 1 and this is your E 2 is equal to 400 volt, E 1 is also here and this angle is 70.5 degree and this is your, this part is I c and this part is your I m and this is the resultant current I 0, right. So, this is a simple and this is the phi, the reference phasor, right. And E 1 is given here, E 1 is given here 2400 because it has to be balanced, ideal case it has to be balanced, right. So, it is 204 volt, here also it is showing 2400 volt, right. Now, EMF equation, these two equations also in the magnetic circuit in general I have given, E 1 is equal to 4.44 f phi m n 1 volts and in the secondary side also 4.44 f phi m n 2 volts, right. So, n 1 n 2 only turns difference are different, but equations are same, right. So, this EMF equation this is given actually in that magnetic circuit I have given, and if you take the RMS value you have to divide it what you call that your in that your what you call in that magnetic circuit, the divided by root 2 everything has been done there, right. So, now if you take this example, a single phase 500 by 1000 volt 50 Hz, then it is also a step down transformer because voltage is getting reduced on the secondary side, has a maximum core flux density is 1.5 Weber per meter square, and on effective your cross sectional area of 50 centimeter square. Determine N1 and N2, a very simple one. You know flux is equal to B into A, you have seen in the magnetic circuit. This is B is the flux density and A is the cross sectional area. So, B is given 1.5 Weber per meter square and A is 50 centimeter square. So, 50 into 10 to the power minus 4 meter square. Therefore, phi m is equal to 1.5 into this your area is equal to 75 into 10 to the power minus 4 Weber. Since U1 is equal to 4.44 phi m N1, we know that. Therefore, N1 will be U1 upon 4.44 F phi m. That will be 500 divided by you substitute, and the if even it is not mentioned, right, generally you take it is a 50 Hz system, F is equal to 50 Hz. So, that is F is equal to 50 Hz is taken, and this is the phi m, right. So, you will get N1 is equal to 300. Similarly, N2 is equal to E2 upon 4.44 F phi m, that is 100 upon 4.44, 50 Hz, F is 50 Hz, and this one you will get 60. So, basically you will get N1 is equal to 300 and N2 is equal to 60. In your what you call, even without using this, if voltage ratio is given, your what you call V1 upon V2 is given, your this is your V1 upon V2 is equal to say N1 upon N2, right, and this is given actually 500 by 100, that will be 5. So, you have got N1 we got is 300. Therefore, N2 is equal to your 300 by 5. Here from here also you can get it, N2 is equal to 60, right. So, this is your N2 is equal to 60. So, thank you very much, we will be back again.